Everyone, welcome back to Chemistry Ado. This is the the third video on experimental techniques. We will continue this chapter. Alright, so just before starting this chapter, I want to mention that two topics from states of matter are left that I'll be covering after I complete experimental techniques. The topics are diffusion and osmosis, not osmosis, just diffusion. But I'll be discussing osmosis as well, and the effect of pressure on melting point and boiling point. I was not able to do them in the states of matter chapter, so I'll be doing it after this experimental techniques. Alright, so last time we discussed distillation, crystallization, centrifugation. Apart from this, we also discussed decanting, sublimation, and other processes for separation. Alright, now we'll be starting with fractional distillation. Now this is a very important process, so you need to pay very close attention. Alright, okay, so let's start with fractional distillation. Fractional distillation. Okay, so in distillation we discussed that there is a fractionating column. Alright, so in simple distillation, what happened was, for example, I had a solid substance dissolved in a liquid. Alright, for example, salt and water, and I actually just heated the solution. Alright, and passed the solution through a condenser. I'm sorry for the bad drawing, I'm just doing it in a hurry. Oh my god, it's very bad. Alright, now I have a thermometer. Alright, I have a conical flask, and I collect the solvent. But what if I have multiple solvents? What if there are miscible liquids dissolved in a solution? Alright, then what will I do? So what I then do is known as fractional distillation. Now I'm going to erase this and start with fractional distillation. Alright, so I'll be drawing the apparatus. Alright, so here is the apparatus that is used normally. Now you need to keep in mind that some things are very similar to simple distillation. For example, the use of these marble chips, first of all as anti-bumping granules, and second of all as stirrers. So I'll not be repeating them. And why is the position of inlet of water and outlet of water in the manner that is shown. And apart from this, the purpose of thermometer here. Alright, however, let's just assume that we have a solution. Let's say two alcohols, any two alcohols. Let's say CH3OH plus C2H5OH. Two alcohols, one is methanol, the other is ethanol. Alright, now they're both soluble with each other, and what happens is that I provide heat. Now it's very important that you know that I have written heat and I have actually not drawn flame. Alright, now why is that so? It's because organic solvents or organic compounds are flammable. They can catch fire. Alright, so that will be a very dangerous thing that if you heat it under direct flame. Alright, so there are three ways in which you can actually carry out heating without causing the organic compounds to catch fire. So ways of indirect heating. Alright, I'll be mentioning them. So first of all, you can use an oil bath or a water bath, oil/water bath. And second, you can use a sand bath. Alright. And third, you can use an electric hot plate. Electric hot plate. Alright. Very important. Very important. Alright. Now if you're asked why is an oil bath used, you'll just say that organic compounds are flammable. Okay. Now this method is based on difference in boiling points. If two substances have the same boiling point, then this method won't work. Alright. So what happens is, for example, let's just say that there are two random substances X plus Y. They're dissolved in each other, and let's just say this is water and the other one is ethanol. Sorry, C2H5OH. Now this has a boiling point of 78 degrees Celsius. This has a boiling point of 100 degrees Celsius. Alright. Now again, you'll be using an indirect method of heating here as well. So what happens is, for example, when I start heating the mixture, the solution, the temperature of the whole apparatus starts to increase. Alright. Now what will happen is that water vapors will form, and water vapors as well as ethanol vapors will form. They will reach the fractionating column and they will bounce back. Alright. Now this will happen until the temperature of the fractionating column is at least 78 degrees Celsius. Why? Because at 78 degrees Celsius, the vapors of ethanol will be able to escape. Alright. Now I'll be also mentioning about the purpose of fractionating column in a bit, but you need to understand the process first. So what happens is that these water vapors escape, these ethanol vapors escape, and the temperature of the fractionating column remains at 78 degrees Celsius until and unless whole of the ethanol has evaporated. So this reaches here, and then it reaches the Liebig condenser, where it is condensed and is collected in a conical flask. Now what I'll do is that I'll remove this conical flask once the temperature on the thermometer starts to rise again from 78 degrees Celsius towards 100 degrees Celsius, and I'll put another conical flask so that water could be collected. Alright, remember not to stopper the flask. Alright, it's very important. So when the fractionating column's temperature will reach 100 degrees Celsius, what will happen is that the water vapors will be able to escape now from the fractionating column, and it will move through the Liebig condenser and into the other conical flask that you have placed. Alright. Now, okay. So let's just start with the purpose of fractionating column. Purpose of fractionating column. Alright, first of all, it separates the liquids on the basis of boiling points. Alright, just as I described the process above. And how does it do that? That it allows liquids with lower boiling point to escape and condenses the liquid with higher boiling point. Alright. For example, in this apparatus, when the temperature is 78 degrees Celsius, it will only allow ethanol vapors to escape. However, it will condense back the water vapors. Alright. So, the purpose, first of all, it separates liquids on the basis of boiling point. Alright. And how does it do liquids with lower boiling point to to escape, liquids with lower, vapors of liquids with lower boiling point, vapors of liquids with lower boiling point to escape, and condense the vapors with higher boiling point, and condense the vapors with higher boiling point. Alright, vapors with higher boiling point. Great. Okay, now the next purpose, now it's also very important. Now the next purpose is that it increases the surface area for condensation. Right now, sometimes the fractionating column is filled with beads, sometimes with other substances, but the main purpose is to increase the surface area so that rate of condensation increases. So increases surface area for condensation. All right. Now there are a few things that you need to keep in mind. Remember that I mentioned that you need to that there are ways of indirect heating. Alright, now I need you to write something along with it. That baths that are used, if you are using a bath, baths used must have a boiling point greater than substance being heated. Alright, being heated. You should not heat, for example, diesel through a water bath, because water bath will evaporate before it reaches the boiling point of the diesel. Alright, so this is important, very important facts. Now moreover, there are a few properties of the solvents that you are going to use. Now properties of solvents. Now this is very important. First of all, they are miscible, of course. Now I need you to think, what could the second property be? Just give it a moment. Just actually think for a moment. Pause the video and think. Alright, I hope you have come to an answer. Now, the second property of a solvents being used in fractional distillation is that they must be having different boiling points. Alright, why? Because it's a process based on the difference in boiling point. You cannot do it on substances which have the same boiling point, because both will escape at the same time. Now you don't want that. Alright. Now I'm labeling a few points here. Alright. So let's just say this is X. This is Y. Alright. This is Z. And this is W. I want you to tell me where in the whole of fractionating column, or this whole apparatus, will there be the lowest temperature? Lowest temperature. And where will there be highest temperature? Just think about it for a moment. Very important stuff. We ask you this in the exams. Think on it. Alright. The highest temperature will be at Y, and the lowest temperature will be at W. Oh, sorry, I wrote it alternatively. Alright. The highest temperature will be at Y, and the lowest temperature will be at W. Alright. Great. Now what's the reason? So as you're seeing here, water has been condensed here. Condensed water is being added into the conical flask. So condensed water has lower temperature, so that's why there will be the lowest temperature at W. And why the highest temperature at Y? Because it is under direct heat. Alright, whenever it's being heated, it will have the highest temperature. Now vapors will escape, all of course, and then it will reach Z, and of course again through the Liebig condenser reach the conical flask. Alright, now that's one portion. I need to make a graph, and I'll be doing it right now. Alright, so this is the graph I want you to complete. So just assume that the substance is being used or ethanol, 3,2H5OH, and water. I'm fractionally distilling a solution of ethanol and water. Please let me know what will be the graph of temperature versus volume of distillate. Just pause the video and think. Okay, I assume that you have gotten to an answer. So at 0 degree Celsius temperature, there will be 0 distillate, because none of the ethanol nor water have evaporated actually and condensed simultaneously. Alright, so the temperature will keep rising, and the volume of distillate will remain 0 until I reach 78 degrees Celsius. Alright, which is the boiling point of ethanol. Now the temperature will remain constant, and the volume of distillate will start to increase. Why? Because the water is being evaporated, ethanol is being evaporated and condensed simultaneously. And if anyone asks why does the temperature remain constant, he should refer back to the States of Matter chapter, in which I clearly told that during change of state the temperature remains constant. Alright, so volume of distillate and temperature for 78. Then after all of the ethanol has evaporated from the mixture, the temperature will start to increase again. It will increase until it reaches 100 degrees Celsius. Alright, now at 100 degrees Celsius, the volume will increase again. So are you seeing that I have made 2 stairs? Alright, so can I draw a conclusion that number of stairs is equal to the number of substances in the mixture? Alright, great. Very important stuff. You need to remember all this. Alright, now I'll be moving on to the uses of fractional distillation. Now there are 3 uses in O-level syllabus. So uses of fractional distillation. Alright, now overall there are 3 uses. First of all, the crude oil, fractional distillation of crude oil. Second, air, fractional distillation of air. And the third one, now it's not basically fractional distillation to be exact, it's more of the use of fractionating column, but I'll be mentioning it here. It's the oxidation reaction. It's a very famous reaction of our chemistry, oxidation reaction, in which what happens is that an alcohol basically reacts in the presence of an oxidizing agent, that is KMnO4, potassium manganate, and heat under reflux. Now you don't need to be baffled by all the fancy words that I'm using. I'll teach them in due course. And it turns into carboxylic acid. Alright, a very famous reaction of our organic chemistry. Alright, now I'll be mentioning it as well here, but I'll be teaching its detail in organic chemistry. Alright, so let's start with the crude oil. Alright, so this is the apparatus that we'll be using for fractional distillation of crude oil. Now I'll be explaining whole of the process, you don't need to worry, but I just want to give you an idea of what actually is crude oil. So when we actually extract oil from the ground, it's not in the form that you can use or that you use in your cars or in your daily life in cylinders, etc. It's actually a mixture of all those stuff, and what we do is that we fractionally distillate the crude oil into its component solutions, its component mixtures, its components, and there are basically 7 components in your syllabus that we'll be discussing. Now you need to know the components in increasing order of boiling points or decreasing order of boiling points, and as well as their uses. Alright, so the first component that is extracted is natural gas, right? Or you can also write gas as well, natural gas. The second one is gasoline, or more commonly known as petrol. Alright, third one is Nafta. Fourth one is paraffin. Now keep in mind that paraffin is also known as kerosene oil. And the fourth one is diesel oil. Fifth one being lubricating oil. Seventh one being bitumen. Right, now down the fractionating column, the size of fraction increases. Now what do I mean by size of fraction? The carbon chain. Now I'm just taking a random number, it's not the true value. Now, for example, if it has, let's say, 3 carbons in its chain, bitumen will have a lot more carbons, let's say 40. I'm not going to draw that, but like you get the idea. That means size of fraction increases. That is what is meant by it. Next, boiling point increases. Alright, that's why they are lower. They are lower down in the fractionating column. And if boiling point increases, then can I say volatility decreases? Now what is volatility? Volatility is basically the ability to evaporate at low temperatures. Alright, so volatility, it actually decreases. Decrease. Alright, so what happens is that I actually enter the crude oil from here and I heat it in a heater. Alright, it evaporates, it starts to evaporate, and then there are cooling jackets here in the fractionating column, set at different temperatures, each according to the boiling point of the substance. Alright, now this portion will be at a, you can say, lower temperature as compared to this one. Why? So that the vapors of gasoline can condense here, and then the vapors of naphtha here, and then the vapors of paraffin here. Now it goes on. Alright, so I'll only draw 3 of them, so that's important. So the vapors are condensed and fractions are collected at different levels of fractionating column, and there are then and you need to also mention that boiling point increases down the fractionating column. right? This is just a special type of fractionating column, but the mechanism remains same. All right, in any type of fractional distillation. All right, now coming to the uses. All right, I need to erase this. Okay, so first of all, the use of natural gas. The natural gas is used for cooking purposes in cylinders, used for cooking purposes. Petrol, used for fuel for cars, used as fuel for cars. Next is naphtha. Now naphtha is very useful. Now what we use it in making soaps, we use it as fuel. It has so much numerous uses that we simply say that it is a feedstock for chemical industry. It's very efficient and it's a very useful fraction. Next is paraffin or kerosene. It's used as fuel for jets. Next is diesel oil, fuel for heavy vehicles like trucks or jeeps. Heavy vehicles. Lubricating oil, as the name suggests, waxes and polishes. And finally, bitumen. Now, bitumen has no particular use. Alright, it's not a very specialized substance that we can use for very specific purpose, and it cannot be used as fuel as well because it has a very high boiling point. As I told, that boiling point increases down the fraction, and at that point combustion becomes inefficient for if you combust bitumen. So what we do is that we use it for surfacing of roads, used for road surfacing along with slag. Now what is slag? This is what I have to teach you in the metals chapter, but just for information right now or curiosity, the slag is obtained from the purification of iron. Alright, I'll teach this in great details. Alright, now this was the use of fractional distillation in crude oils, in the separation of crude oil. Now I'll also teach you in the process of oxidation. Now remember that I'll be teaching the air portion in the chapter of air and oxygen. Alright, not here, because that's a detailed process, a long process. It needs a separate chapter, right? Okay, so let's start with oxidation. Now, as I told you, it's a very famous reaction of organic chemistry. We'll be dealing with it a lot. Very famous reaction. What happens is that if I take any alcohol, alright, and I react it in the presence of a oxidizing agent. Now, if you don't know the meaning of the word oxidizing agent, you don't need to worry. Alright, just remember it and heat. Alright, so that we have a carboxylic acid. So what we do is that we use a fractionating column. I'm sorry, not a fractionating column, a Liebig condenser here. Alright, so as I told you before, that the process is not a lot related to fractional distillation, but it does have the use of Liebig condenser. That's why I'm teaching it here. Alright, so what we do is that we actually I have one of the worst drawings. Oh my god, it's so awful. I'm embarrassed actually. Alright. Alright, so what happens is that I add the alcohol and potassium manganate from here. This is an electric hot plate. Alright, and this is a condenser. Now water comes in from here and goes out from here. Again, to not make it a gravity fed process. Alright, so what happens is that water, that you have the contents here. Now the process requires heat, alright, but you also know that alcohols are volatile, like they evaporate at very low temperatures. So that's why we are using this apparatus. Otherwise, we don't need to. Alright, so what happens is that as soon as I start providing it heat, the vapors try to escape. Alright, but when they reach the condenser, they condense. Alright, and they start to come back inside the round bottom flask. Alright, so this happens and happens until the temperature is hot enough for alcohol to react with potassium manganate and form carboxylic acid. So that's almost the whole of the process. And what will be the observation? Observation would be that potassium manganate would turn from purple to colorless. Alright, from purple to colorless. Okay, so that's the observation of the reaction. And sometimes we ask you the purpose of condensation. So what is the purpose? It prevents alcohol vapors from escaping. As well as stirs the vapor. Alright, and what do I mean? What happens is, as you can see, vapors evaporate, they condense, fall back into the round bottom flask, then other vapors start to evaporate, then fall back. This stirs the solution. This actually makes the process more efficient. Alright, so it stirs the vapor. Okay, so that's all for fractional distillation in experimental techniques of O-level chemistry. Alright, I'll see you guys in the next video with chromatography, and then we'll do the two remaining topics that I told you about, as well as the processes for collection of gases, their acidity, their basicity, the density, and methods of collection of gases. And then we'll finally end the chapter with some questions. Alright, so see you guys inshallah in the next class. Until then, I hope you're enjoying the lectures, and please subscribe and like the channel. Bye.